Question 18. This question is about reactions of ions and compounds of transition elements. A student carries out 2 experiments on a solution containing chromium 3 plus 6 water. Experiment 1. The student added an excess of aqueous ammonia to a solution containing chromium 3 plus 6 water. The 6 water are the 6 ligand with a coordination number of 6. That means 6 water is bonding to the central atom by dative covalent bond. And that's why the charge on the chromium with the water is still 3 plus. So what happened is you're adding excess ammonia, which means the ammonia would displace water and then replace it with ammonia. So NH3,6. So the ammonia would displace water and replace it with ammonia. So that's what we'll expect here. And that's why it turns purple until a purple solution is formed. So this is a purple solution. Experiment 2. The student carries out the following reaction sequence. Step 1. Ammonia is added slowly to a solution of chromium 3 plus with water as a ligand. In a boiling tube, a gray-green precipitate is formed. Well, so because sodium hydroxide is added, then the OH ion will displace 3 water. Hence, you get 3 OH ion. But this is OH minus. So chromium is 3 plus, and you got 3 minus here because it's 3 of them. And therefore, no charge. Remember, chromium is 3 plus. Water is a ligand. It doesn't have any charge on it. But OH minus has a charge of -1 times 3. That's -3. -3, we cancel the 3 plus. -3, we cancel the 3 plus. And then you got no charge. So sometimes you can write it as CrOH3, same thing as that, and 3 water, hydrated chromium hydroxide. Step 2. An excess of sodium is added to the boiling tube, sodium hydroxide. Step 2. An excess of sodium hydroxide is added to the boiling tube. The precipitate dissolves, and a green solution forms containing a 6 coordinated complex ion. So now, what happened was you added excess sodium hydroxide, and the excess will knock off the rest of the water, and hence you're going to get 3 more OH minus. Hence you're going to have 3 minus. Because you got 3 plus and 6 minus, you're going to get 3 minus charge. Step 3. H2O2 hydrogen peroxide is added to the mixture, and the boiling tube is heated. A yellow solution is formed. Well, H2O2 hydrogen peroxide is an oxidizing agent. That means it will oxidize chromium. So chromium has been oxidized from +3 to +6. So you can see we've added oxygen there as well. So you're going to get CrO4 2 minus. So the overall charge here for chromium, overall charge is 2 minus, which means we know oxygen is -2. -2 times 4 is -8. And the overall charge is 2 minus. So you need +6. +6 minus 8 will give you -2. Hence, I'm going from +3 to +6. So that's been oxidized. So therefore, H2O2 is an oxidizing agent. Step 4. The solution in the boiling tube is acidified. The solution now contains Cr2O72 minus aqueous. So this is orange in acid. So question 1. What is the formula for the complex ion in the purple solution that formed in experiment 1? Formula is CrNH3,6. 6 of the water has been replaced by ammonia. That's 3 plus. Because the ammonia doesn't have any charge. It's only got lone pairs. And the lone pairs are used here as a dative covalent bond. So that's 3 plus 6 still. So that's 3 plus still. 2. Suggest an equation for the reaction in experiment 2, step 1. Include state symbols. So if you get chromium chloride and you add ammonia and sodium hydroxide to chromium chloride, you get chromium hydroxide plus sodium chloride. So that will be the equation for that experiment. You could write the ionic equation for that one, and that will be, we could say that is Cr3 plus aqueous plus 3OH minus aqueous, and that will give us CrOH3 solid plus 3 sodium chloride aqueous. So that's the ionic equation there. So that's ionic. So we could write the ionic equation for that one by saying Cr3 plus aqueous plus 3OH minus aqueous, and that gives CrOH3, which is solid, and that will be the ionic equation. 3. Draw a 3D diagram for the shape of the complex ion that forms in experiment 2, step 2. Include the charge of the ion. So we got the central atom, which is the chromium. So we got the central atom, chromium, and we've got 6 hydroxide ion, and this one here is the wedge, which means it's pointing out of the plane towards the observer, and this one is pointing out of the plane. This one is pointing back into the plane, the backwards of the plane. This is pointing to the backward of the plane. The plane is a screen, it's a 2D screen, and this one is lying in the plane, which is another, this one is lying in the plane as well. So this is 6 coordination number, because you got 1, 2, 3, 4, 5, 6. So it's bonded to 6 ligands, and that's the formula again. Cr, chromium hydroxide 6, 3 minus. So that'll be 3 minus there, because chromium is 3 plus. Each one of these is minus 1. 3 plus, we cancel 3 minuses, you're left with 3 minus. That's why it's 3 minus. 4. What is the formula for the ion that causes the yellow color in experiment 2, step 3? So the formula is chromate 6 plus. That's a chromate 6 plus, and then CrO4 2 minus. So the formula is CrO4 2 minus. 5. State the color of the solution that forms in experiment 2, step 4. The color is orange, and it is Cr2O7 2 minus. So you're starting from 2 CrO4 2 minus plus 2H plus, that's acidified, that is an acid, and that would form Cr2O7 2 minus plus H2O. So that is orange color. That's orange color. B. Vanadium ion have 4 common oxidation states, as shown in table 18.1. And that shows the colors of the ions in aqueous solution. So vanadium 5 plus is yellow, that's vanadium 5 plus. Vanadium 4 plus is blue. Vanadium 3 plus is green. Vanadium 2 plus is violet. 1. Complete the electron configuration of vanadium 3 plus ion. So vanadium electron configuration is this, because vanadium V has 23 electrons and the mass is 50.9. So because of that, it's got 23, and here they are. That's 2 plus 2, 4, 10, another 4, another 10, which makes it 3, that's 23. Now it's going to lose 3 electrons, that's why it's 3 plus. So the first 2 electrons it will lose is 4s2, because 4s2 is lower than 3d3. So we'll lose that 2 there, and then you'll be left with 1 to lose, so we'll lose 1 from there. So it will have left 3d2. So the V3 plus is going to be that 2. The student added excess ion to a solution containing vanadium O2 plus aqueous ion, and observes that the color of the solution changes from blue to green and then to violet. use the relevant standard electrode potential. Pay attention to the keyword standard electrode potential shown in the table 18.2 to explain this observation. Here are the standard electrode potential. The reason why they call them standard electrode potential, it's actually a standard reduction electrode potential. This is standard reduction electrode potential. The reason why they call them standard reduction electrode potential is because these are reduction. You can see they are reduction because when you add electron, it's a reduction. That's V2 plus to V0. That's a reduction. Ion 2 plus to ion 0. That's a reduction. So that's why these are called standard reduction electrode potential. Standard reduction electrode potential. These are the electrode potential here. So these electrode potential are not showing oxidation, they're showing the reduction. So from the table and the question given, VO2 plus, which is blue, turn into V3 plus, which is green, and V3 plus turn into V2 plus, which is violet. So what we're looking for is that we're looking for that one. That's what we're looking for. And that one is this one here. VO from the table is number 4. VO2 plus aqueous plus acidified, which is 2H plus an electron, because that should then give V3 plus water. Well, the charge has to balance, right? That's 2 plus 2 plus again, 2 times plus, that would be 4 plus minus 1, that would be 3 plus on this side, and that's 3 plus on this side because water has no charge, so that's balanced. So charge is conserved. Now we know charge is conserved. The standard reduction electrode potential for this equation is plus 0.34. The more positive it is, the more this reaction will be, the more it will go to the right. Now this reaction, that means this is what we call reduction because it's gaining electron. So that's a reduction potential. This table is giving us a reduction potential. Standard electrode reduction potential. Ion 2 plus, in this case, if this one is taking electron, something must be giving it electron. So this will be giving it electron. So that's the, so therefore, why is this giving the electron? Because this is more negative and that's more positive. The more negative will be reversed. So this equation will be reversed. It will be ion 2 plus going to, this one is, sorry, this is ion solid. Let's just get that right. That's ion solid. So if I just remove that slowly. So that's ion solid. Right, because this is reduction potential. So it's going from the 2 plus to 0. So that's reduction. So this is the, from the table redox system. We're looking for number 2 and number 4. This is number 4, and this is number 4, and this is number 2. So what was the question? The question was V02 plus, which is blue, turn to green, V3 plus. And V3 plus then turn into violet. This is green and turn into violet, so that's V2 plus. So how is that happening? Well, first of all, so we have the potential here. We got this from reduction potential table, and these are the potential for it. Now, so we picked the Fe2 plus, which is number 2. Fe2 plus gaining electron to go to reduce to Fe, and the reduction potential is minus 0.44. This one here is VO2 plus acidified, obviously you added H plus, that's 2H plus electron, give you V3 plus water. This will balance if you work it out. The charge has to be balanced. 2 plus 1 times 2, that's plus 2, which means plus 4, minus 1, because it's minus, that would be plus 3. On this side is plus 3, so charge is balanced. But the more positive, that means this reaction stays. That means this will be gaining electron, and then the V will be reduced. Right, so this is V3 plus. This one is plus 2, and oxygen is minus 2. Minus 2, what can I add to minus 2 to get plus 2? So I have to add plus 4. So this is plus 4. V is plus 4. Plus 4 minus 2 will give plus 2. So V is plus 4 here, and V is plus 3 here. So it has been reduced, as it's a reduction potential. Now, so what we now need to do is compare their potentials and see what happens. So the first potential that we're going to compare is this. So you can see this one here going to there, V02 plus, blue, and going to V3 plus. The potential for V0 going to V02 plus, going to V3 plus, that potential, yeah, which is 0.34, that's what we meant by that. So this is the E value indicating starting from there, that's the start, and as it finish, so that journey from there to there, the potential is 0.34. That potential is greater than the one for the iron. So if you look at the iron, starting from iron 2 plus, going to iron 0 solid, that potential is minus 0.44. So that's what the answer will be really. We're saying that that potential is greater than that. And that's what this is saying. Also, the potential going from V3 plus to V2 plus, I haven't written that potential here. V3 plus to V2 plus, this is number 3. That potential is minus 0.26. So that potential for this one here is E, right, V3 plus to V2 plus. That potential is equal to minus 0.26. So what we're saying, that potential is greater than the ion potential, because minus 0.26 is more positive compared to minus 0.44, because minus 0.44 is more negative and this is more positive. Because this is more positive, that will stay. That means that will stay. So that will go definitely from there to there, because it's more positive. It will be a reduction compared to the iron. So that means iron will be, iron will be supplying the electron to make that happen, because this has to reverse because it's more negative. The more negative one will always reverse, and the more positive will stay. So let's write that down. So the more positive electrode will shift to the right, that means that will stay compared to iron, and the more negative, the less positive electrode will shift to the left. This one is less positive, so it's more negative, so this will shift that way. So that means this will reverse. So it's going to start with iron solid and go to iron 2 plus. So this is the full equation. So this is the half equation. So this one here is what you called reduction, because the plus 4 going to plus 3. So that's reduction equation. And this is the electrode potential, standard reduction potential. And this one will be the voltage there. So that's the standard reduction potential there. This one is reversed because it was minus, because it was going from that. But now we've reversed it. So now this is now releasing the electron, and this is receiving the electron. So now what we need to do is to balance this situation here. So this is the reduction equation and oxidation equation. The reduction equation, obviously this one stays because it's more positive and that was more negative. And then we have to reverse this one. So it's now reversed, which means the potential will be reversed. So now it's more positive because it's not going that way. Before it was going that way. We always put the electron to the left as a reduction, standard reduction potential. Now, because we've reversed it, the electron is on the right, this is now oxidation. So all we now need to do is to balance the number of electrons. So the electron here is 2 minus. That has to be 2 minus as well. We have to multiply everything by 2 to make the electron balance. So now I've multiplied everything by 2, which means that 2 will balance with that 2. So this is half equation. That's the other half equation. So what we now need to do is add them together and complete the equation. So now we add all this left-hand side together, that and that together. Don't forget the 2 electrons cancel out. So that plus that plus that is that one here. On the right-hand side, we add them together. So that is these 2 here and that water. And so now this is what we call the full overall equation. That was the half equation, and this one is oxidation equation. This is reduction equation. Now we need to add their potentials. So the potential in this case will be 0.3 volts plus 0.34 volts plus 0.44 volts. Altogether will be 0.78 volts. This is the equation that was required, and because it's going from blue to green, this is green, that's blue. So that's the equation that was required. But I have to obviously balance it off with this one, right? In order to get the full equation there. But the equation that was required was that one. C, iron 2 gluconate, which has that formula, is the active ingredient in some brands of iron supplement. C, iron 2 gluconate, and that's the formula, is the active ingredient in some brands of iron supplement. A student carries out an experiment to determine the mass of iron 2 gluconate in 1 tablet of an iron supplement using the method below. Using the method below. Stage 1. The student crushes 2 tablets and dissolves the powdered tablet in dilute sulfuric acid. Stage 2. The student makes up the solution from stage 1 to 250 centimeter cube in a volumetric flask. Stage 3. The student then titrates 25 centimeter cube portion of the solution obtained in stage 2 with 0.002 mole per decimeter cube potassium permanganate. 7. The student obtained a mean titrate of 13.50 centimeter cube. In this titration, 1 mole of manganate 7 iron react with 5 mole of iron 2 iron 1. Explain why the student used 0.02 mole decimeter cube per decimeter cube potassium permanganate 7 solution for this titration rather than the more usual concentration of 0.02 mole per decimeter cube used in manganate for titration. Well, a large titrate which leads to a small percentage error or uncertainty. So you would use a large titrate because it will lead to small error. So you want small error rather than a large error. That volume is large. If you were to use 0.02, the volume would be about 10 times less, so that would be 1.35. The volume would have been 1.35. 1.35 is small. 13.50 is large. So with a large titrate, you will get a small percentage error. Use the student's result to determine the mass in milligram of iron 2 gluconate in one tablet. Give your answer to 3 significant figures. So we've got the acid base and salt here. The concentration of the base, which is potassium permanganate, so we're going to use 1 mole of potassium permanganate, that's KMnO4. So 1 mole of potassium permanganate should give us concentration times its volume. We know the concentration is 0.002 times 10 to 0.0135 for the volume. And this is in decimeter cube, so you do the 13.5 divided by 1,000 to get that. And so you get this mole. That's the number of mole. So the next thing to do is actually to write down the equation for this reaction. So let's do that. The manganese, that's manganese O4 minus, we just ignore the potassium because potassium is plus and manganese will be minus. So that's a minus. And so we ignore that, and then we acidify it. That means we add H plus. Okay, when we did that, we get, let's go for the reaction here. So you get Mn2 plus, that'll be aqueous, plus H2O. So what we need to do is to balance this one here. You see 4 oxygen here. So you can see you need 4 water because of the oxygen is 4. You have to put 4 here to get 4 oxygen, which will give you 4 water. So that's what we're going to do here. So I'm going to put 4 there. And next thing we need to do is now to see, we now need 4 times 2 is 8 hydrogens. There's 1 hydrogen here. So we need to multiply that by 8. So we put 8 here, right? So after that, that's how you balance this stuff. And then we need to balance charge. This is plus 2 here, and that's 0. So on the right hand side is plus 2. On the left hand side, I've got minus 1 overall, because that's overall minus 1. And this is plus 8. Minus 1 plus 8 is plus 7. Plus 7 here, plus 2 here. Obviously, I need to add minus 5 to plus 7 to then get plus 2 here and plus 2 there. And that's why the way to add it is to add electrons. So I'm going to say plus 5 electrons. So that's the way to add it. So now let's see. It should be balanced now. We get plus 2 here, we get plus 2 there. Plus 8 minus 5 will be plus 3. Plus 3 minus 1 is plus 2. So that's balanced. Right. We need to then do the same for iron. So let's look at the iron that we're using. So the iron we're using is, because remember, if this is taking 5 electrons, iron should be given 5 electrons for that to take. But we are using iron 2 plus, right? Going to iron 3 plus, right? And that's plus 1 electron. So this is what happened with the iron. You get the iron 2 plus going to iron 3 plus, releasing 1 electron. Now we need 5 electrons. So we have to multiply this by 5. So that has to be multiplied by 5 to make it balanced. So I'll multiply this by 5 and multiply that by 5 and multiply that by 5, which means that now it's ready for full equation. The first one here was the half equation. So if I draw a line there underneath, so this one here is half equation for what we call reduction, because you can see it's gaining 5 electrons, and this one is releasing 5 electrons. That's oxidation, and we add them all up now. So that means for every 1 mole of manganese we need 5 mole of iron. So that's what we need, 5 mole of iron. So let's actually balance this up and finish that. So we're gonna have MnO4 4 minus, right, plus 5 Fe2 plus 8H plus, and that will give, right, so you got Mn2 plus 5 Fe3 plus, and that's it. That's what you're going to get. But what about the water? You got the water as well, plus 4H2O. So that's what you're going to get there. And once you get that, now we can now finish solving our the mole for iron. If we know the mole of potassium permanganate is 2.75 times 10 to the power minus 5, the mole for iron is going to be 5 times that, because you see, for every 1 mole, you got 5. So now, for iron 2 mole, which is going to be 5 times 2 times 10, 2.7 times 10 to the power minus 5, will be equal to 1.35 times 10 to the power minus 4 mole. Right, so that's from this equation, you see 1 to 5. All right, so now we know the iron, mole of iron, but in the tablet, we've only got 1 iron in it, 1 iron in the tablet structure, in the formula. So if you write down the formula down for the tablet, we know the formula is going to be C12H22, then the Fe is only 1, and oxygen is 14. So really, for the 1 mole of iron we just calculated here, that's 1 mole of iron now in that tablet, because so that is a mole of that iron in that tablet. So we add up the water to 250, so 25 centimeter cube is what we use, and that gives us 1.35 times 10 to the power minus 4 mole. And so what we did was, to get the 250 back, we need to times it by 10, which will give us 250 centimeter cube, and we have to times that by 10 as well, so times 10, and when you times it by 10 you get 1.35 times 10 to the power minus 3, because it times it by 10. Now, so what we now need to do is we need to work out the mass of iron in the tablet. So if we divide it by 2, because we got 2 tablets, so that one is for 2 tablets, remember? So we need to calculate for 1 tablet. So we need to, this is for 2 tablets. So we need to divide this by 2. So if I divide it by 2, just to make, so let's divide it by 2. So if I divide it by 2, we get 6.74 times 10 to the power minus 4 mole. So that's the number of mole in it, 1 tablet. If that's the number of mole in 1 tablet, we need to work out the relative molecular mass for the compound here, and that turned out to be 5.8 grams per mole. So that is this one is the mass of that. And so now we need to work out the actual mass using the mole mass relative molecular mass formula. So we know mole is mass over relative molecular mass. We know the relative molecular mass, we know the mole, we want to find the mass. So what we need to do is to say, right, the mass is going to be mole times relative molecular mass. Okay, so if you plug the values in, which is for the mole, so we're going to get 6.74 times 10 to the power minus 4 times 5.8. And when we get that, what do we get? So we get 0.30046 grams. Okay, so once we get that, what we now need to do is, that's the mass of 1 tablet. So don't forget, because you got 1 mole of iron in gluconate. You got 1 mole of iron in gluconate. Because that's basically 1 mole of iron here. That's 1. This one is 22 moles of hydrogen. That's 12 moles of carbon. This is 14 moles of oxygen. This is 1 mole of iron. That's why we used that 1 mole. That's 1 mole of iron now. And then we divide it by 2 for 2 tablets. That's why. So here, that's the mass M, with the mass M equal to that. So what we can then do is to write it in milligrams. So the mass M of iron in tablet is going to be 300 milligrams. So that'll be 300 milligrams.